Okay, so we begin our second lecture on the structural dynamics class, in which the focus is on the single degree of freedom system, as you see here on the top of the board. Now, it's important to note that our interest on the single degree of freedom system is connected to the fact that what we will develop here will carry over to the understanding and the computation of behavior in multi-degree of freedom systems. Because it's not because we want to do something very easy that only has one degree of freedom that's why we're looking at this. There aren't many, single degree of freedom systems in practice, although many things can be approximated sometimes. But really the value of this is much more than its immediate application on the purely single degree of freedom system. Now, we have a mass M, a spring, an idealized spring, massless K, an idealized dashpot C, and we've already seen that the equation of equilibrium of this mass in the horizontal direction would read like this: mq double dot cq dot kq is equal to pt. Now, we begin by looking at the case of homogeneous, at the homogeneous equation, which is when there is no excitation. So, in this case, we would have, I don't know what happened to this. Let's see. We would have mq double dot plus cq dot plus kq equal to 0. And we refer to this as the homogeneous equation, right, of motion. Now, because it is equal to 0, it is evident that we can divide by m, and therefore we can write q double dot plus c over m. This is just, of course, a convenience. Q dot plus k over m, q equal to 0. Okay? Now, this is a second order linear differential equation, and we can propose that the solution, let me erase here and even here, and in fact I will copy this one here on top to give myself more room. So q double dot plus c over m q dot plus k over m q is equal to 0. Okay? Now, we wish to see what is the solution of this equation, so we begin by, as we normally do in differential equations, by postulating a solution. So we say, let's see what happens if we inspect this form, a e to the st, where I don't know what a is, I don't know what s is, but I want to see if the form of the solution is like this, what happens when I substitute it over there. Now, taking two derivatives of this, all we get is s squared. Taking one derivative, all we get is s. And so it immediately follows that taking one derivative and two derivatives and substituting in the equation, we would have a times s squared times e to the st plus c over m times a times s times e to the st plus k over m times a times e to the st, and all of that would be 0, right? Two derivatives, one derivative, no derivatives. So from here we can see that a and e to the st are common factors of s squared plus c over m times s plus k over m. And this must be 0. Okay? Now, paste here again to have a little more space. And if we look at this, oh no, let me copy one thing, which is we are looking at a postulated solution A e to the st. So one possibility to make this 0 is that A is 0. But if A is 0, this just means Q is 0, that means nothing is happening, and okay, that's true, but it's trivial. The other possibility, you might say, is that e to the st is 0, but e to the st cannot be 0, right? For all time, for any value of s except minus infinity. And so we discard that case and we say, okay, the way in which this can be 0 is by the term inside this brackets being 0. And therefore we say that the solution of the homogeneous equation demands that the second order polynomial s squared divided by c over m s plus k over m should be 0. Okay? So now we've imposed a constraint on the s value of the equation. Now, this is a second order polynomial, and we all know that the solution will have two roots. Let's say we call them s1 and s2, which would be, I mean, people write it in different forms. I'm going to use the form minus b over 2, which is this way, which works. The form I'm using already assumes that there is a, well, it doesn't assume. I'm accounting for the fact that the coefficient on the square is 1. So plus or minus the square root of b over 2 squared minus c, k over m, right? And so we have this situation for the solution of the roots that go here. Now looking at that, we see that this term here is going to determine the nature of these roots as to whether they are real or complex. If this term inside this square root is positive, then we have two real roots. If the term inside this square root is negative, then this will be an imaginary term, and this will be two complex conjugates roots, right? Something plus something, I, something minus something, I. All right, now, so we can say, to say it formally, that c over 2m squared minus k over m, right, if it is less than 0, then this is going to be imaginary, and we have two complex conjugate roots. And if this is greater than 0, we will have two real roots, right? That is, this will be real. The division between less than 0 or greater than 0 is obviously that it is equal to 0. Now, in the particular case when this is equal to 0, we still have two real roots because this is 0, right? So we get minus c over 2m plus or minus 0, which means that the root is then repeated, right? This thing of repeated root sometimes is confusing to people, but let's just say in the particular case when this thing is exactly equal to 0, which is the dividing line, we have, actually let's just say one real root, but then we have to put repeated. As I say, that can be confusing at first, because what do you mean repeated? I mean, yeah, I can see it's plus or minus 0, but what do you mean? Well, we will see that there is a physical meaning to this particular thing, that it will be best illustrated, well, no, maybe I can say it right away here. Let me see. What happens when the root is repeated, I can say it I guess right away, is that the root does not only make the polynomial equal to 0, but it makes the derivative of the polynomial equal to 0. okay? That is, if we take the derivative of this, you can see that the derivative of this is 2s plus c over m, right? 2s plus c over m. And so if you say that that is equal to 0, you get that s is equal to minus c over 2m, right? So this value of s makes the derivative of the polynomial equal to 0, and you can see that that value of s also makes the polynomial equal to 0, because, let's see, what's the deal? If we want to make this thing is equal to 0, no, I'm sorry, I've made an error, or not. Let's see. If I want to make this equal to 0, I have z over 2m. No, I'll have to correct this. C over 2m is equal to the square root of k over m. Okay? Hold it. Let me pause it for a second.